Woo woo, all aboard the math train. Let's learn about continuous functions. The classic definition of a function having a limit at a point is as follows. Suppose you've got a function f of x. You've got two particular real numbers, a and L. Now, a is going to represent a number in the domain of the function, and L is going to represent a number in the range of the function. Not exactly, but that's basically the idea. Now, if for any epsilon, which is positive, there is another corresponding delta, which is positive, so that for any x whose distance to a is positive, so x can't equal a, but it's less than delta, so x is close to a but not equal to it. If you have this and that guarantees the distance from f of x to L is less than epsilon, notice this distance can be 0, that's fine, as long as it's less than epsilon. Then we say the limit as x approaches a of f of x equals L. Here's basically what the picture is going to look like. So we've got a function f of x. So as we throw down our axes, our function looks something like this. Okay, this is the generic picture I pretty much always draw for functions, a nice cubic. Now here perhaps is a, something down in the domain. Now here might be a corresponding value L in the range. What we've done is we've said for any epsilon which is positive, and the end result of this definition is the absolute value of f of x minus L, the distance from f of x to L, must be less than epsilon. So I'm going to represent that as an allowable distance, L plus epsilon to L minus epsilon, in the range, because we're talking about comparing a number to L. And this defines a certain tube, I like to call it, of possible y values or possible outputs. Okay, what comes after saying for any epsilon which is positive, we say there exists a delta which is positive, so that if the distance between x and a is less than delta but positive, then I guarantee the distance from f of x to L is less than epsilon. So let's look at this picture here, and what we see is there a corresponding a minus delta to a plus delta down in the domain, so that any inputs down here correspond to outputs in this tube? Yes. Based on the way I've drawn this picture, if I input anything down here, distance delta in the domain, what I get out is distance less than epsilon in the range. So for now, what we're going to say is that this limit exists in the classical sense, because we are going to have some alternate versions of the definition, and this definition with the epsilon and the delta playing against one another, we're calling the classic definition or the classical definition. Here's a corresponding definition based off of sequences. Again, we've got f of x as a function, a and L are real numbers, they're standing for the same things they did before. But notice now, the definition changes. If for any sequence, so that all but finitely many of the terms are not a, and the limit is a. So I have a sequence, this is down in the domain, approaching a, but not constantly equal to it. Maybe a few terms of the sequence are equal to a, but only finitely many. So past a certain point in the sequence, you don't see a, but you do approach a as a limit. Whenever you have that, then you have the corresponding sequence in the range must be converging to L. Then you say the same thing. The limit as x approaches a of f of x equals L. And once again, what we're going to do is we're going to draw a picture and sort of see what's going on here. So here's our function, f of x. Here's going to be our point A down in the domain. And here is going to be our corresponding value L in the range. What we do is we take a sequence of points down in the domain, xn. It's a sequence, maybe it's equal to a couple of times, but only finitely many times. So the sequence, let's just imagine it converging that way. Then what we get out is a sequence of points in the range. This height, let me actually just draw them pushed over to this vertical line. This height, then if I plug in this x value, I get out this y value. If I plug in this x value, I get out this one. So the sequence in the codomain or in the range is approaching the height of L. No matter how I try to draw a sequence of points converging to A down in the domain, what I'm going to get out in the range is a sequence of points that must be converging to L, to that height there. If that is what you can guarantee, any sequence converging to A in the domain produces a corresponding sequence converging in the range to L, then you have the same thing. Okay, and we're going to call this the definition of a limit existing in the sequence-based sense, because we're basing this off sequences, not off the classic epsilon delta. Yep, I mean, that's going to be kind of a theme, as I said. Yeah, they are both going to be the same definition exactly. And here we have it. They are the same. No matter whether you go with the epsilon delta, aka classic definition of a limit existing, or the sequence-based version, they are equivalent, so we need to prove that they each imply one another. So what we need to do is assume the limit exists in the classical sense, the epsilon delta version. We're going to show that it exists in the sequence-based sense. The gist of the proof is as follows. So what we're going to assume is that the limit exists in the classic sense. So we have our function. Okay, I keep drawing nice, smooth, what we'll learn is called continuous curves. It doesn't have to be, but it just makes the picture nicer. So what we get to assume is that here is my choice of A, here's going to be my choice of L. We get to assume that for any epsilon which is positive, eventually we can trap the distance of f of x to L to be less than epsilon. In other words, I'm going to set this little tube from L plus epsilon down to L minus epsilon. That once we pick this epsilon, what necessarily happens is that there exists some delta so that if x minus a is in between 0 and delta, then, in other words, from a minus delta to a plus delta, if I pick any x in here, we are trapped to have x's within plus or minus epsilon of L. That's what we get to assume. Then what we need to prove is the limit exists in the sequence-based sense. So what we're going to then try to prove is if xn converges to a and xn equals a only finitely many times, then f of xn must converge to L. So what we get to assume is that we have a sequence converging to A down here in the domain. But now observe what happens to that sequence. Eventually, it's trapped from plus or minus delta of A. Because the sequence converges to A for any positive distance, and in this case that's going to be delta, the sequence is eventually that close to A. But what did we get to assume? If x is trapped within delta of A, then f of x is trapped within epsilon of L, which is exactly going to give us what we want about that sequence there. So let's go ahead and prove it. We get to assume the limit exists in the classic epsilon delta sense. Now we assume I have any sequence at all, x sub n converging to A, and only finitely many of them are equal to A, which means if any of them are, there's a last one. So what we're going to do is we're just going to start the sequence there. In other words, get rid of finitely many terms that are equal to A. This never affects limits. Getting rid of finitely many terms has no effect at all on the limit of a sequence. So let's just assume that none of them are equal to A. And we get to assume that they're converging to A. Now we let epsilon be positive. Our goal, remember, is to show that f of x sub n is converging to L. So let epsilon be positive, and our goal is to show that eventually f of x sub n is epsilon close to L. But we assumed the limit existed in the classical sense. So provided x is delta away from A, f of x is definitely epsilon away from L. Since the limit of x sub n is A, and delta is positive, there is an index past which every term of the sequence is delta away from A. But if you're delta away from A or closer, then f of u is epsilon or closer to L. So since x sub n is delta distance from A, f of x sub n is guaranteed to be epsilon distance from L, and this is for all indices past a certain point, and that point being determined by the fact that x sub n was converging to A. And that's exactly the definition that f of xn converges to L. So that's half the proof. We assumed if the limit exists in the classical sense, it does exist in the sequence-based sense. Now what we have to do is prove the other direction. Okay, so let's go ahead and do it. But we're not going to prove that if the limit exists in the sequence-based sense, then it must exist in the classic sense. Instead, we're going to prove the contrapositive. Assume the limit doesn't exist in the classic sense, and then we'll show that it doesn't exist in the sequence-based sense. We gotta make sense, however, of what it means to not have a limit in the classic sense. So the original definition would have been, for any epsilon which is positive, there exists a delta which is positive, so that if the distance from x to a is between 0 and delta, then the distance from f of x to L is less than epsilon. Now what we need to do is we need to negate this entire thing. So what we get is there exists an epsilon which is positive so that for any delta which is positive, now I have a conditional statement. How do you negate that? True hypothesis and false conclusion. So we get that the distance from x to a is positive but less than delta, and the distance from f of x to L is bigger than or equal to epsilon. That's the negation of less than, bigger than, or possibly equal to. What would that look like? There exists a positive epsilon. Okay, so first of all, here's our, same picture. Here's going to be x equals a. Here's going to be y equals L. Okay, so there exists a positive epsilon which applies to distance to L. So let's go ahead and draw whatever special epsilon this is. This now doesn't change. Okay, this was not an arbitrary epsilon, it was one particular epsilon. But now, for any delta which is positive, no matter how small we want, there will exist some point x that's in this interval, but not in the tube we drew above. So this picture isn't really accurate, but there's going to be some point down here in the domain so that f of that is outside this. But that's true for any delta which is positive. So if I pick smaller and smaller and smaller deltas, what we're going to get are points, that color's not very visible, what we're going to get are points closer and closer and closer to A, but f of them is consistently outside L plus epsilon to L minus epsilon, and therefore the sequence can't be converging to L. We're going to get a sequence that does converge in the domain, but the corresponding sequence in the range is not converging to L, and therefore we're going to violate the sequence-based definition of limits existing. So let's get to it. We're assuming the limit doesn't exist in the classic sense. So there is some epsilon, so that for any delta, there is some x, which does satisfy the required distance in the domain, but does not achieve the desired distance in the range. Epsilon is fixed and can't be changed, but delta was arbitrary, so I'm going to make a sequence of them. For delta equals 1, 1/2, 1/3, and so forth, there will always exist some particular x that is delta away, and delta is now the sequence 1 over n, delta away from A in the domain, but f of xn is at least epsilon away from L in the range. So notice, I can apply the squeeze law to that inequality. 0 is less than the distance of xn to A is less than 1 over n. As n goes to infinity, xn must be converging to A. So since xn is converging to A, we would think that f of xn must converge to L, but for every single one of these xn's, the distance to L was at least epsilon. So the distance is never less than epsilon, and therefore the limit of f of xn either doesn't exist, or if it does, it sure as heck isn't L. So since we found a sequence converging to A in the domain, but f of that sequence was not converging to L in the range, the limit does not exist in the sequence-based sense. So what we proved was, if the limit does exist in the classical sense, then it does exist in the sequence sense. And now on this slide, if the limit doesn't exist in the classic sense, it doesn't exist in the sequence sense. So the two definitions are equivalent. Both notions have to do with closeness. And yeah, so the goal is always get f of x close to L. That's always part of the definition of the limit being L. Then you have to make x close to A. Exactly right. Basically, intuitively, here's what limits are. If you want the limit as x approaches A of f of x to be L, you're saying if I make x sufficiently close to A, then I guarantee f of x is as close as I want to L. So here are some results you can prove about limits. Suppose that f of x and g of x have limits as x approaches A. The limit of f of x is going to be f, capital F, and the limit of g of x is going to be capital G. Notice that A is the same between both of these. X is approaching the same value. Then the limit of the sum, product, and quotient of the functions do exactly what you would hope. They're the limit of f plus the limit of g, or the limit of f times the limit of g, or the limit of f over the limit of g, and of course you don't want to divide by 0. Now you can If you really, really want, prove all of these using the epsilon delta definition, but oh gosh, why bother? We already have theorems that state exactly this when it comes to sequences. They're very, very quick proofs using the sequence-based definition, and we've already shown that the two definitions are equivalent, so go ahead and do it that way. We can also discuss what are called one-sided limits. So the limit as x approaching a of f of x equals L required us to say, suppose the distance from x to a is less than delta, but that doesn't specify whether x has to be bigger than a or less than a, just within distance delta. Okay. If, however, we specify that the x's are bigger than a, whether we're doing the epsilon delta definition or on this slide as written the sequence version, now we have a sequence converging to a, but every term is bigger than a. But if the rest of the definition doesn't change, okay, so for any sequence converging to a, provided they're all bigger than a, you guarantee that f of that sequence converges to L, then you say the limit as x approaches a from above of f of x equals L. The equivalent version in epsilon delta says, suppose the distance from x to a is less than delta, but x is bigger than a, which you can see by dropping the absolute value, that is basically what we get. If 0 is less than x minus a, you just add the a over and you get a is less than x. So now we have x is delta close to a, but bigger than a. So these are either called right-sided limits or limits from above. You can do a similar definition to get left-sided limits or limits from below just by requiring that x be less than a in the epsilon delta version or xn less than a in the sequence-based version. One thing that's worth pointing out, by the way, every picture I've drawn has been a nice curve that I draw in a little smooth motion like this. But what if that isn't exactly what we have? So now, what I'm going to do is I'm going to draw something else, like maybe this. Okay, so here the function looks like a nice curve, but at this particular value of x, it has this weird jump. Okay, and I'm going to call this a. The limit as x approaches a of f of x is this height up here. Because in the epsilon delta version, remember that the distance from x minus a was going to be less than delta, but definitely positive, so x can't equal a. So what happens at x equals a does never play into the definition of a limit existing. And in the sequence-based version, the sequence converging to a can only equal a finitely many times. Past a certain point, it's never a again. And again, you're going to see that what happens to the function at a is never actually important. And if you had a picture that looked something like this, now I have a function. Let's just say this is x equals a, this is y equals L1, and this is y equals L2. What you'll see is that the limit as x approaches a from below of this function is L2, but the limit as x approaches a from above of this function is L1, because if I restrict myself to only using x's bigger than a, I simply see the value L1 over and over again. So any sequence of values converging to a strictly from above, the sequence f of that x value is just going to be L1, 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 and so forth, and constant sequences have that limit. But if xn is approaching a from below, then f of those is just going to see L2, 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 and I'm going to get that limit there. So the pictures that I have been drawing up to this point are always just nice, quick to draw smooth curves, but that's not really required for limits to exist. It's just a convenient way to draw pictures. Here's a nice useful result. Suppose f is a monotone function. It's either monotone increasing or monotone decreasing. On an open interval a with supremum a, that's the supremum of the interval, not of the function, then the limit as x approaches a from below of the function exists. And there's a similar result for right-sided limits approaching the infimum of the interval, or the left endpoint of the interval. In other words, I've got an interval which is open a. It has a supremum, which I'll just call little a. The function f is monotone increasing, let's say. So the function doesn't have to be continuous, but if it has these jumps, it's got to just go up. Okay. Then the claim is the limit as x approaches a from below of f of x exists. Now I certainly can't take a limit from both sides because I don't even know if the function exists on the right. So I'm not going to attempt to apply a two-sided limit here. Since this right endpoint lowercase a is the supremum of the domain, I'm just going to let the x approach a from below. And the claim is that f of x will have a limit, possibly plus infinity. I'm including that as a possibility here. All right, so what we do is let xn be any sequence which is monotone increasing with limit a. Then f is a monotone function, which means f of xn is monotone. If f is monotone increasing, then since xn is increasing, f of xn is increasing. If f is a decreasing function, then xn being increasing would mean f of xn is decreasing. But either way, since I took a monotone sequence with limit a, f of xn is definitely monotone one way or the other. Now I have a monotone sequence, therefore it has a limit, which might be plus or minus infinity, but monotone sequences have limits. So suppose xn and yn are two distinct sequences, both monotone increasing, both with limit a. Then f of xn has a limit, we'll call it L sub x, and f of yn has a limit, we'll call it L sub y. But if I just union the two sequences together, xn and yn, and consider taking it in the order that it's increasing, it takes a little bit of work to show that this is possible to do, by the way. But since xn and yn have the same limit a, it is possible to union them together and enumerate them in increasing order. Now that I have an increasing sequence with limit a, this new sequence also gives a new limit. Okay? But the sequence xn is a subsequence of this union, so its limit must be the same limit as the one overall, because if the sequence given by xn and yn has limit, let's call it capital L, then L sub x is the limit along a subsequence. And if the limit exists overall, every subsequence must have the same limit. So whatever the limit is of this union, xn and yn together, the sequence just along x's must have the same limit, and must the sequence just along y's. It's also a subsequence of that union. Therefore, Lx and Ly have to be the same number. So for any monotone increasing sequence towards a, f of xn has the same limit. We've just shown any two monotone sequences increasing towards a will have the same limit, f of xn or f of yn will have the same limit. So for any monotone sequence with limit a, f of xn has the same limit. And we have shown in a previous exercise that if any monotone subsequence of a sequence has a limit, then the sequence has a limit overall. So for any sequence converging towards a, all monotone subsequences have the same limit. F of xn approaches the same limit a, and therefore f of xn overall will have a limit because all monotone subsequences of f of xn have the same limit. Therefore, if you have a monotone function and you are approaching a real value, there is always a limit, possibly plus or minus infinity. All right, here's a sample problem for you to go ahead and attempt. It's simpler than that last one. Suppose f, g, and h obey this inequality, etc., etc. Go ahead and work on it. Well, hopefully you used the squeeze law. Okay, moving on. Now we get the real definition that we were trying to get to in this section. A function is called continuous at a if not only does the limit as x approaches a of f of x exist, but the specific number, capital L, that we use on the right-hand side happens to be exactly f of a. So the limit as x approaches a of f of x is equal to f of a. That's the definition of being continuous at a. Yeah, the definition only says take what you used to have as this definition of a limit existing and use a specific value for that limit, f of a. One thing to point out is that a is the limit as x approaches a of x. If x is approaching a, then x is approaching a. So you can view this, you can view this as the limit commuting with the function. The limit as x approaches a of f of x is f of the limit as x approaches a of x. So continuity at a point is a commuting property of functions with limits. We kind of extend this definition to say if you're continuous at every point in a set, then we just say the function is continuous on the set. A function being continuous on the set A just means continuous at every point in A. Let's work on a couple of sample theorems. The function f of x equals x and a constant function g of x are both continuous on R. So what this is really saying, if I have two functions, one of them is f of x equals x, that if you pick any value of A, and then here is the value of f of A, well, f of A is just A because f of x equals x. If I take any sequence xn approaching A, can I guarantee that f of xn is approaching f of A? And then we want to do the same thing with constant functions as well. But because the functions are nice and explicit and pretty simple to work with, we're going to see this doesn't take a whole lot of work. Also, we're going to go ahead and work through with the classical definition rather than the sequence definition just to change things up a bit. So let A be arbitrary. We're trying to show these functions are continuous at every real number. So pick a real number A and let it be totally arbitrary. We want to show it's continuous at A, so we have to show for any positive epsilon some stuff happens. So let epsilon be positive. Then we have to show that delta exists, and I'm just going to pick delta to equal epsilon. Okay. Now what we say is, suppose x is a real number whose distance to A is less than delta. Well then, the distance from f of x to f of A, well, x is f of x and A is f of A. So the distance from f of x to f of A is just the same thing as the distance from x to A. We assumed the distance from x to A was less than delta, and we also set delta to equal epsilon, and overall, you get that the distance from f of x to f of A is less than epsilon. For the constant function, it's even more straightforward. It doesn't even matter what x and a are. G of x and g of A are both c. That's the same constant. And the distance from c to itself is 0, and epsilon was positive, so 0 is definitely less than epsilon. So for any real number A, we were able to satisfy the classic definition of continuity at A, that the limit as x approaches A of f of x equals f of A, and the limit as x approaches A of g of x equals g of A. For f of x, it's just because f of x is x and f of A is A, and by setting delta equal epsilon, it was pretty direct. The constant function's even easier. Delta is essentially irrelevant because the distance of g of x to g of A is always 0, and 0 is always less than epsilon. Now here's a function that isn't continuous everywhere, called the sine function, not S-I-N-E, not trigonometry, but S-I-G-N. If the number is positive, the sign is considered 1. If the number is negative, the sign is -1. And the sign of 0 is 0. So this function is not continuous at 0. If we graph the function, here's what it looks like. So for x negative, the value is -1. For x positive, the value is 1. But at x equals 0, we are exactly equal to 0. This is the sine function, S-I-G-N. So why is this function not continuous at 0? Well, f of 0 is 0. So if the function is continuous at 0, then classically what we'd have to say is for any epsilon, no matter how small, let's imagine it very, very small, so to 0 plus epsilon, 0 minus epsilon, there must be some corresponding delta so that down in the domain, anything I plug in here, the value is trapped to be epsilon close to 0. But we can see that that doesn't happen. No matter how close I go from the left, my value is -1, and no matter how close I go from the right, my value is +1, which is not going to be as close as I want to the desired value of 0. And if we're doing the sequence-based version, we can do this the same way. Just by saying, suppose you take a sequence converging to 0 from the left, then f of that sequence is a constant -1, not converging to 0. Similarly, if you take a sequence from above, f of that sequence is a constant 1, not converging to 0. And that's the gist of the proof. We're actually going to mix those two sequences together. Let x sub n be -1 to the n over n. So -1, +1/2, -1/3, +1/4, -1/5, +1/6, and so forth. These values are in between -1/n and +1/n. By the squeeze law, -1 to the n over n therefore converges to 0. Okay? But f of xn is just flopping back and forth. Xn goes between positive and negative values, so f of xn is just going between plus or minus 1, which is not converging to f of 0, aka 0. So even though we have a sequence converging to 0 in the domain, we don't have a sequence converging to f of 0 in the range, therefore the function is not continuous at 0. Yeah, jumps of functions can kind of be seen to be discontinuities. We found x very close to 0. We found this sequence converging to 0, where f of the sequence was not converging to f of 0. That's really how you show something is not continuous at a point. Now there's a sort of third definition of continuity, the topological definition. Okay. Remember, topology was all this stuff about open and closed and compact sets. So suppose you have f of x being a function and a is some point, which is again going to be down in the domain. If for any open set containing f of a, the pre-image f inverse of capital A, which is just all real numbers so that f of x lands in A, if that set is also open, then we say the function is continuous at the point in the topological sense. This is a bit more abstract. What we're saying is, pick a point in the domain A, corresponding point in the range f of A. Take any open set you want that contains f of A, and look at all possible points in the domain that get mapped there. If that is also an open set, regardless of which A you took, as long as it was open, then you say the function's continuous at A. So I do want to point out this inverse image of a set is not quite the same thing as a function inverse. We are misusing notation, but it is quite common. So if you picked a single number, f inverse of y, in this notation you mean all possible points so that f of x is equal to y, even if there's more than one of them. So a function that isn't invertible, you can still use this notation for pre-images, they're called. We're going to use this definition once. Okay, prove the function 1 over x is continuous everywhere except for 0. So pick a point that isn't 0, so f of a is 1 over a. We need to say for any open set containing 1 over a, the pre-image b must also be open. And remember, the pre-image is all points so that f of x lands in this set A. The goal is to show that the set B is open. The way you show a set is open is to take any point in that set and show you've got some wiggle room around it. So pick a point in B. We'll call it y. B, remember, was the pre-image of A, which means that any point in B gets sent into the set A. So if y is an element of B, f of y is an element of A, but f of y is just 1 over y. Y can't equal 0 because I have to be able to plug it into the function. It's in the pre-image of a set. I can send it somewhere. Since y isn't 0, it's either positive or negative. We're just going to go ahead and assume that it's positive. Okay, the proof is similar if it's negative, but we're just going to split it into two cases and just address this one. A was an open set. So any point in A has wiggle room around it. 1 over y is in A. Therefore, there is a delta so that I can wiggle 1 over y left and right by delta and still be a subset of A. I'm going to go ahead and assume delta is small enough so that 1 over y minus delta is still positive. 1 over y is positive because y is positive. So I can wiggle to the left a little bit and still be positive. So I can still be in the set A. And I can make it even smaller if necessary to guarantee that 1 over y minus delta is positive. Also, I can assume that 1 minus delta y is positive. That's really just multiplying that inequality we have right there by the number y. And since y is positive, multiplying by it does not cause the inequality to change. So now what we're going to do is we're going to let epsilon equal this crazy monstrosity here. One may verify, which is math speak for it takes a little bit of work. It's a lot of computation, but you should be able to do it. that if epsilon prime is smaller than this number, we have all of the following, okay? So epsilon prime is smaller than that mess, which means negative epsilon prime is bigger than negative that mess, which means y minus epsilon prime is bigger than y minus that mess, which means the reciprocals are smaller. So there's your left inequality. Getting these middle inequalities is just a matter of doing some arithmetic. You can also show, again, since epsilon prime is less than epsilon, which was that nasty looking expression, that 1 over y plus that is bigger than 1 over y plus that nasty mess. And then it's a matter of doing some arithmetic to get to the other end there. Again, this takes some work, but this all falls under general algebraic manipulation that you should be able to put together. So now what we see is, as long as the distance of x to y is less than this epsilon prime, f of x, another 1 over x, is in between 1 over y minus epsilon prime and 1 over y plus epsilon prime. But therefore, it's in between 1 over y plus delta and 1 over y minus delta. That's what the inequalities above show. If x is in between these two possible y values within epsilon prime of y, then 1 over it is in between 1 over y plus epsilon prime and 1 over y minus epsilon prime, which we've just shown means you're in between 1 over y plus or minus delta. So f of that must be in A, meaning all of those points are in the preimage of A. So the entire interval y minus epsilon prime to y plus epsilon prime is in A. In B, sorry, is in the preimage of A. All of those x's can get sent to something in A, therefore all those x's are in the preimage of A, which we called B. So any point in B, which we called y, has a little wiggle room around it, epsilon prime. I can move left or right by epsilon prime and still be in the preimage of A, so any point in B has wiggle room around it, therefore B is open. And I agree, this is not the most straightforward way to prove this function is continuous. The metric version, the classic version, is kind of okay to work with. But this is a nasty way to try to prove any specific function is continuous, that the inverse image of open sets is always open. Yeah, they are equivalent. If f is not continuous in the topological sense on a set, then it is not continuous in either of the other two senses on that set. Now the proof is not going to be as bad as you'd think, trust me. Here's what we do. Suppose y is a point in f of a. Now what we need to prove, okay, remember f of x is not continuous in the topological sense. So what we get to assume is that there is an open set containing y whose preimage is not open. So there's an open set, call it U. It's an open set containing y, and its preimage is not open because we assumed the function was not continuous in the topological sense. Now what does it mean for f inverse of u to not be open? It means there's at least one point in the set with no wiggle room around it. I'm going to let x be that special point somewhere in f inverse of u that has no wiggle room around it. In other words, no matter what positive delta you pick, if you move left or right by delta, there's going to be at least one point not in f inverse of u. I'm going to call that special point x sub delta. For any delta, there is some point x sub delta that is within delta of x, but is not in f inverse of u. But if x isn't in f inverse of u, then f of x sub delta is not in u. Remember, f inverse of u is all the points that get sent to u. If you're not in f inverse of u, if x sub delta is not in f inverse of u, then f of x sub delta is not in u. So f of x delta is not in u, but u is open and y is in u. So there is some wiggle room around y that remains in u. Some wiggle room being epsilon. Notice this epsilon only depends on y. It's the wiggle room around y that is in u. But since f of x delta isn't in u, it can't be within this wiggle room around y. So the distance of f of x delta to y must be at least epsilon. We're going to use that to violate continuity at y. Now here is a picture that's going to hopefully make this point a little clearer. Okay, so I've got something up in the range which I've called y. It is achieved as f of something. There is some open set u which contains the point y. And I'll just draw a little open interval along the y-axis. Okay, here is my set u. What I do is I ask, what's the pre-image of u? F inverse of u is all points x that are somehow trapped in between this little wiggle room around y. So maybe there are some x, certainly this x is inside that interval of y's. Maybe there are some x's over here that also get mapped into there. Maybe some x's all the way up here if the function does something like it comes back through this range of possible y values. That's fine, whatever. But we're assuming this set is not open. If the set isn't open, then there is some point in this pre-image set, and let's just say it's like right here, so that no matter what plus delta or minus delta, some particular x, okay, this is not an open set, so any wiggle room I attempt, there's going to be some point, which we call x sub delta, that's not in f inverse of u. Which means when I send this up to the range, f of x is not in u. So f of x is either too low or too high. But this is doable for all deltas. So there's no possible way to put a sort of delta distance around a certain point and be forced to be within epsilon of y. Because I just keep getting points that are delta distance away down in the domain, but more than epsilon distance away up in the range. Similarly, if the function f of x is not continuous on A, then it's not continuous in the topological sense. This will close the proof that the topological definition is equivalent to the other ones. So suppose y is an element of A, and f of x is not continuous there. In the classical sense, there is an epsilon, so that for any delta, there is a point delta distance away from y, but epsilon distance is achieved up in the range f of x delta compared to f of y. This is the given that it is not continuous at y. There exists an epsilon, so that for any delta, there exists a point whose distance is within delta of y, but whose distance in the range is at least as large as epsilon. So the open set f of y minus epsilon, f of y plus epsilon violates topological continuity. Basically the same picture we had on the previous slide works here. The pre-image of this interval can't contain anything on both sides of y because all those intervals contain these x sub deltas that are very, very close to y, but whose image in the range is epsilon distance away from f of y. So there's three different definitions we have here. The topological definition, which is kind of a mess to work with, the classical definition, the epsilon delta one, and the sequence-based version. Why do we bother with so many different definitions of continuity? The topological definition is actually tremendously useful for certain ways of generalizing this idea, and there are going to be some times where a theorem is actually easier to prove using the topological definition compared to the other ones. If you want to discuss continuity of functions and you're not just talking about the real numbers, if you're talking about a general thing called a topological space, well, the topological definition is what you want to use. The classic epsilon delta one involves thinking about the distance between numbers. So anytime you have what's called a metric, a way of measuring distances, this definition can be pretty handy. The sequence one is really, under most circumstances, the same as the metric one, under most reasonable ones that anyone other than a specialized topologist would consider. The sequence-based version is going to be equivalent to the metric one, but it just makes some proofs easier. We already saw that earlier. There was a statement about limits of sums of functions and products of functions, and the sequence version just made the proofs fall right out compared to the classic epsilon delta one. So this might just be a little easier in certain scenarios. All right, after a long, interlude of a bunch of abstract nonsense, here are some practice problems. You want to show these functions are continuous on certain sets, and notice, because you have three definitions and they're all equivalent, you're free to pick for each problem whether the sequence version, the metric version, or, for some particular reason, the topological definition are easiest for you. So pause, work through the problems, go ahead and throw down a comment without profanity in it. Can't tell you how long I spend scrubbing all the profanity-laced comments from my YouTube channel. Okay, so hopefully you were able to do these. Great, let's move on. Here is an example we will work through together. This function f of x is 1 if you plug in a rational and 0 if you plug in an irrational. It's called the indicator function of the rationals. In general, an indicator function is something that's 1 on a set and 0 off the set. So this is 1 on the rationals and 0 off the rationals, so it's the indicator function for the rationals. We claim this function is not continuous anywhere. Yes, it is definitely possible for a function to be continuous nowhere. Here's what the function looks like. So down in the domain, if I plug in a rational number, I get out a value of 1. If I plug in, like maybe I plug in 1/3, okay, f of 1/3 equals 1. However, f of, say, pi over 9 is 0, because that's an irrational number. But what do I know about every interval of the rationals, of the reals, sorry? It has rational numbers in it, but it also has irrational numbers in it. The rational numbers don't fill up any intervals. So no matter how close you look, there's always going to be points that are irrational evaluating to height 0, and there's always going to be points that are rational evaluating to height 1. This function goes back and forth between a value of 1 and -1 so often, in a sense, that you can never narrow down what it's close to. No matter how far you squeeze in the domain, no matter how small an interval you try to draw, it's going to have rationals and irrationals in it, so f is going to take the value 0 and 1. So let a be an arbitrary real number. We're trying to show the function is not continuous anywhere, so pick an arbitrary point and show it's not continuous there. For any interval containing a, it's going to contain both rational and irrational numbers. So for any interval a minus 1 over n to a plus 1 over n, I'm going to pick a sequence, x sub n. If n is even, pick x sub n to be rational and in this interval. If n is odd, pick x sub n to be irrational and in this interval. These intervals always contain rationals and irrationals, so sure. Now I have a sequence of x's squeezing down towards a, alternating between rationals and irrationals. So xn converges to a because the distance of xn to a is no larger than 1 over n, and 1 over n goes to 0. So xn converges to a. But f of xn keeps going back and forth between 0, 1, 0, 1, 0, 1, 0, 1, which doesn't converge. Specifically, it can't converge to f of a because it doesn't converge to anything. So yeah, this function is not continuous at a, and a was arbitrary. This function is not continuous anywhere. That's going to finish up this video on a basic definition of continuity, limits of functions. Come on back, continuity is going to be a really important topic. We're going to keep talking about it.